So this is about pure bending, which I was talking about. So in this case, this is the vertical plane. So the moment is acting in the vertical plane. That means it is acting about this neutral axis, z-axis. When the moment is acting about z-axis, which we have calculated in the last semester in your solid mechanics theory of simple bending, FB or F or sigma is equal to m by I into y. A famous flexor formula or bending formula, which is m by I equal to F by y or sigma by y is equal to E by R. This we have calculated. Okay. Now, if it is about vertical axis, then what is there here? M is bending moment, what is acting about z-axis, and I is moment of inertia about z-axis, about which the moment is acting, and y is the distance from the z-axis. Similarly, when the moment is acting about y-axis, here, now M is moment acting in the z plane or about y-axis, and I is moment of inertia about y-axis, and instead of y here, now you get distance from y, that is z. Okay, so you get bending moment in two different planes. So it is called unsymmetric bending. If it is not along the axis of symmetry, we call it as unsymmetric bending. This, in other words, we call these two axes as principal axis of inertia. About this axis, that is along the axis parallel to width, you get maximum moment. Hello? Sorry for that, there is a problem in the internet. Yes. Now we'll continue again. So m by I into y is the bending stress when the moment is acting in the vertical plane, that is about z-axis. Okay. Now we'll go to what is unsymmetrical bending. Now, when the plane of loading or bending does not lie in a plane that contains principal axis of the cross section, then the bending is called unsymmetrical bending. So now you should know what is principal axis. I was discussing about principal axis. For symmetrical sections, the axis of symmetry, these two are the principal axis. This is along the width of the section. If you take moment of inertia about this axis, bd cube by 12, b into d cube by 12, and about this axis, if you take this as x-axis and this as y-axis, about x-axis moment of inertia is bd cube by 12, about y-axis it is dv cube by 12. So dv cube by 12 is the minimum moment of inertia which the section has, and about x-axis bd cube by 12, it is a maximum moment of inertia about any axis it has. Suppose if you take any axis like this passing through CZ, the moment of inertia will be in between bd cube by 12 and dv cube by 12. So principal axis of inertia are the axis about which either the moment of inertia is minimum or moment of inertia is maximum. Okay. So now if the plane of loading is along the principal axis, one of the principal axis, then it is called symmetrical bending. If it is not along the axis of principal axis of inertia, then we call it as unsymmetrical bending. So here you get the two cases. One is section is symmetric like this, and load is inclined like this. It is passing through the CC of the section, but it is inclined. It is not along the axis of symmetry, but it is along the line which is inclined at an angle, some theta say. Now it will cause two components. It will have one vertical component and one horizontal component. Now this is first case where you get unsymmetrical bending. The second case is the section is unsymmetric. Though the load is along the vertical axis, the section is unsymmetric. So in this case also you get unsymmetrical bending. So these are the two cases. One, the section is symmetrical. but the load line is inclined to the principal axis. This is the case. And second one, the section itself is unsymmetrical and the load line is along any centroidal axis. So in the second case, load is along the centroidal axis, but it is section itself is unsymmetric. There is no axis of symmetry here. If these two are identical, then there will be axis of symmetry along the two corner join two corners. Along this, you'll have the axis of symmetry, and that will be IU, that is principal axis. Now, in this case, when the load is acting like this, it has two components. One is cos theta component, and the other one is sin theta component. So W is the load acting. W cos theta is vertical component. W sin theta is horizontal, which is shown here. W is the load acting inclined at an angle theta to the vertical. So W cos theta is the vertical component and W sin theta is the horizontal component. So if a load W is acting on a simply supported beam of span L, what is the maximum moment you get at the center? Which is equal to WL by 4. If you call this as WL by 4, M equal to WL by 4. Now, when a load of W cos theta is acting, the moment will be W cos theta into L by 4, which you can write it as WL by 4 into cos theta. So WL by 4, if you call it as M, it is M cos theta. So M cos theta is vertical component, and similarly W sin theta into L by 4, bending in the horizontal direction. So this one W cos theta causes bending in the vertical direction like this, and W sin theta causes bending in the horizontal direction like this. Okay, so W cos theta causes bending moment about horizontal axis, and W sin theta causes bending moment about vertical axis. Okay, so these two moments you'll have. One is about x-axis, the other one is about y-axis. Now, before going further details about the unsymmetrical bending, let us look at what is moment of inertia, principal axis of inertia, and product of inertia. You all know moment of inertia at this time. It is second moment of area about an axis, right? So if you take x-axis, if you consider an elemental area here, some area dA, its distance from x-axis is say y, then its first moment about x-axis is dA into y, and second moment is dA into y square. So y square dA is the first moment of second moment of elemental area about x-axis. So if you want the second moment of area, whole area about x-axis, you integrate it. So Ix, moment of inertia, or Ixx, it is also known as Ix or Ixx, is equal to second moment of area about x-axis is integral y square dA for the entire area, right? Similarly, Iy, moment of inertia about y axis is integral x square dA for the entire area. Then another term, product of inertia, Ixy, is the moment of area about both the axes. So if you consider again elemental area dA, its moment about x-axis is y dA, and if you take moment of that moment about y-axis, it is y into x dA, that is xy dA. So product of inertia is integral xy dA for the entire area. Okay, so product of inertia is integral xy dA. Now we require Ixy also here when you want to find the axis about which the moment of inertia is maximum. For a regular section like rectangle, BD cube by 12 is the maximum moment of inertia, and DB cube by 12 is the minimum moment of inertia we know. And about any axis, arbitrary axis we take, the moment of inertia will be in between these two values. Okay, but if it is an irregular object or an unsymmetrical section, how we calculate maximum moment of inertia, and what is the axis about which you get the maximum moment of inertia? If you want to find that, we calculate or we take an arbitrary axis like this, which we call it as transformation, that is rotation of axis system, that is xy is the original axis system. Now it is rotated by an angle theta to get x dashed and y dashed y dashed. So now you are transforming xy axis to x dashed y dashed, which is inclined at an angle theta. So y dash is inclined at an angle theta with y. Now, if you want to calculate x dash, moment of inertia about x dash, is equal to ix about this axis cos square theta plus iy sin square theta minus ixy sin 2 theta. Ix is moment of inertia about x-axis, iy is moment of inertia about y-axis, and ixy is product of inertia about xy axis system, right? So and theta is the angle of rotation of this axis system. Okay. Now this, if you rearrange these terms, cos square theta is cos 2 theta plus 1 by 2, right? And or 1 plus cos 2 theta by 2, and sin square theta is 1 minus cos 2 theta by 2. So if you write that and try to rearrange these terms, you get ix plus iy by 2 plus ix minus iy by 2 cos 2 theta minus ixy sin 2 theta. This is ix dashed, that is about new x-axis. Moment of inertia is expressed in terms of moment of inertia about x-axis, y-axis, and the product of inertia ixy and the angle theta of the new axis with old x-axis. This is theta. Okay. Similarly, iy dashed, moment of inertia about new y-axis is ix plus iy by 2 minus ix minus iy by 2 cos 2 theta plus ixy sin 2 theta. And product of inertia about x dashed and y dashed axis is now ix dashed y dashed, which is equal to ix minus iy by 2 sin 2 theta plus ixy cos 2 theta, or you can also write it as ixy cos 2 theta plus ix minus iy by 2 sin 2 theta. If you look at these equations, if you recall your principal stresses chapter, you get similar expressions. When sigma x is the normal stress in x direction, sigma y is the normal stress in y direction, and tau xy is the shear stress, then normal stress on any plane, oblique plane, sigma theta is given by sigma x plus sigma y by 2, sigma x minus sigma y by 2 cos 2 theta plus tau sin 2 theta, or tau xy sin 2 theta. So this is similar equation. Only difference is in place of ix, sigma x, sigma y, and tau xy, now we have ix, iy, and ixy. And here in place of plus, now we have got minus. So ix plus iy by 2 plus ix minus iy by 2 cos 2 theta minus ixy sin 2 theta. There plus tau xy sin 2 theta is there, but now here it is minus ixy sin 2 theta. And this is ix plus iy by 2. Instead of plus, here you get minus, and here instead of minus, here you get plus here. So this is the equation for, or this is the expression for I by about new y-axis, right? Then ix dashed y dashed is the expression similar to your tau theta. Tau theta is given by tau xy cos 2 theta minus sigma x minus sigma y by 2 sin 2 theta. So instead of minus, now we have plus ixy cos 2 theta plus ix minus iy by 2 sin 2 theta. So this is similar to your the stresses on an oblique plane, which we studied in principal stresses chapter. So what was the idea of calculating normal stress and shear stress on an oblique plane? There, normal stress sigma theta, if you get it, from that you can calculate what is the maximum normal stress which you get on any plane. How do you get that? Tau sigma theta by tau theta is 0, which gives you theta value corresponding to the maximum normal stress. And if you substitute the theta value again in the sigma theta expression, you get maximum normal stress, which we called it as major principal stress. Similarly, minor principal stress. In the same way, now we have got ix dashed here, ix plus iy by 2 plus ix minus iy by 2 cos 2 theta minus ixy sin 2 theta. Now, this if you differentiate with respect to theta and equate it to 0, dou ix dashed x dashed by dou theta is 0, gives you ix minus iy by 2 cos 2 theta when you differentiate minus 2 sin 2 theta minus ixy sin 2 theta when you differentiate 2 cos 2 theta. So if you equate that expression to 0, you get tan 2 theta is equal to ixy by ix minus iy. So this expression is used to calculate, is minus, of course, minus 2xy by ix minus iy. This expression is used to calculate tan 2 theta. From tan 2 theta, you get sin 2 theta and cos 2 theta values. And if you substitute back in this, cos 2 theta and sin 2 theta values corresponding to tan 2 theta minus 2ixy by ix minus iy. That gives you ix maximum, which we call it as iu. And iuu or iu. When you substitute tan 2 theta or corresponding to tan theta, if you calculate cos 2 theta and sin 2 theta, and if you substitute these values, now you get iu equal to ix plus iy by 2 plus square root of ix minus iy by 2 whole square plus ixy square, and iv is equal to, that is minimum moment of inertia, is ix plus iy by 2 minus square root of ix minus iy by 2 whole square plus ixy square. So these are similar to your major principal stress and minor principal stress. Sigma n1 is sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by 2 whole square plus tau xy square. Similarly, sigma n2 minimum normal stress is equal to sigma x plus sigma y by 2 minus square root of sigma x minus sigma y by 2 whole square plus tau xy square. So same expressions in place of sigma x, sigma y, tau xy, we use ix, iy and ixy to get the principal moments of inertia. This maximum moment of inertia, minimum moment of inertia. So these are important. If these axes, if you can identify these axes, and if the plane of moment is applied along these axes, or the loads are applied along these axes, then it is going to be symmetrical bending. If the plane of loading or plane of bending is not along these axes, or if this is not contained by the plane of moment, it is called unsymmetrical bending. So when unsymmetrical bending is there, now you can look at this particular diagram. So here, this is UU axis, this is VV axis. That means you get UU axis means maximum moment of inertia about this, and VV axis means it is minimum moment of inertia you get about this axis, right? Now this is x axis and this is y axis. So loading is applied along y, or moment is acting along y, a plane containing y axis. So it is not along the VV or UU. So it is called unsymmetrical, or it produces unsymmetrical bending. So now what we have to do, again, if you want to get the bending stresses, or if you want to calculate the bending stresses, resolve this into two components. This is theta. So m cos theta will be along VV plane, or in the VV plane, which acts about UU axis. mv is m cos theta, which acts about UU axis. Similarly, mu is m sin theta, which acts about VV. Here you should be very careful. The component of this moment, which is in the vertical plane, that acts about horizontal axis normally, right, or UU axis. Component in the VV plane acts about UU axis, and component in the UU plane, which acts about VV axis. So when you find out the stress due to mv, that is m cos theta, you need to use iu, moment of inertia about UU axis. So moment about UU axis is, or moment in the VV plane is m cos theta, that is mv, divided by iu, moment of inertia about u or UU, and distance from UU, that is v. So mv by iu into v, that is the bending stress which you get at the point P. mv, that is moment about UU axis, or moment in the V plane, moment about UU axis, by moment of inertia about UU axis, into distance from UU axis, that is v. Okay. Similarly, the other moment in the UU plane is acting about VV axis. So mu, that is m sin theta, divided by IVV into distance from VV axis is u. I hope it is clear, right? So when you use mv divided by iu, m by I into y, that is the formula. So m is mv here, by iu, moment of inertia about neutral axis, it is uu now, or axis of moment, axis about which moment is acting. mv by iu into v, and the other one is mu by IV, moment of inertia over V into U. So this is the formula which you get. Okay, mv by iu into V and mu by IV into U. And coming to the signs, now if the loading is in the vertical direction and if it is a simply supported beam, it causes compression top and tension bottom, you know. So moment is about this axis, it is sagging type of moment. You get compression top and tension bottom. So the stresses above this particular axis, UU axis, is compressive, and below this axis is tensile. Similarly, this moment, the other moment is acting, the loading is acting like this, and if it is a simply supported beam, it bends convex towards left side. And so convex towards left side and concave towards right side. So to the right of this, it is compression, left of this, it is tension. So when there is a simply supported beam like this, when it from top, when it is loaded, it bends this way. So top compression, bottom tension. When it is loaded like this from horizontally from this side, now it bends this way. So compression this side and tension, compression to the right and tension to the left. Or the same load, if it is acting this way, it pushes the member like this. So compression this side and tension right hand side. Okay. So that is how you decide the signs. This we will discuss again when we talk about it, or when we discuss the problem. Okay. Now, to determine the neutral axis, unlike the case of the simple bending or symmetrical bending case, here the neutral axis is not one of these axes, but you need to determine the neutral axis. So what is neutral axis? It is the axis along which or at which the stress is zero or the resulting stress is zero. So now, or the tension is the resulting stress is zero. So now what we do is the stress due to both the moments mu and mv. The stress due to moment in the mu plane is mu by iv into u, distance from vb axis is u, plus mv by iu into v. mv is moment in the v plane by iu into distance from uu axis is v. Will give you the total stress or resultant stress. When you equate this resultant stress to zero, then mu is mu sin theta, mv is mv sin v cos theta, mv cos theta. So mu is m sin theta and mv is m cos theta. If you substitute those values and take the m common or take the m outside, then here you get u sin theta by iv, and here v cos theta by iu is equal to 0. So v cos theta by iu is minus u sin theta by iv, or v is equal to minus iu by iv tan theta into u. So this is the form y equal to mx, v equal to some constant times u. So this equation is of straight line. So neutral axis is a straight line where the net stress is zero, is a straight line. Okay. Now these v and u, if you observe the previous diagrams, what is v by u? V is distance from uu axis and u is distance from uu axis. So what is v by u? V by u gives you, then if you call this slope alpha, tan alpha, right? So v by u is tan alpha. So tan alpha equal to v by u is equal to minus iu by iv into tan theta, where alpha is the angle made by the neutral axis with uu axis. Tan alpha is equal to minus iu by iv tan theta, where iu is the maximum moment of inertia IV is the minimum moment of inertia, or moment of inertia about UV axis, moment of inertia about VV axis, and theta is the angle made by UV axis with the plane of loading, or XX and YY axis, right? So this is how you calculate the position of neutral axis. So here, if you look at this particular diagram, this is YY, this is XX, this is UU, and this is VV, and this is angle alpha. The tan alpha is equal to minus IU by IB tan theta. Gives you this alpha value, and this is your neutral axis, along which the resultant stress is 0. So this is how to find the neutral axis. So tan alpha is equal to minus IU by IB tan theta. So we will be calculating IX, IY, IXY, and then IXY, the product of inertia you'll have only for unsymmetrical sections. For symmetrical sections, it is 0. Because if it is symmetric about the area is symmetric about x-axis, y is 0 for that, right? Or if it is symmetric about y-axis, x is 0. So integral xy dA, x or y is 0 means the product is 0. So for symmetrical sections, it will be 0. Product of inertia is 0. And IU and IV are IX and IV themselves, right? So to determine the IU, IV, you require, if it is unsymmetrical section, you require IX, IY, and IXY. So using IX, IY, and XY in the formula which we have used, IX plus IY by 2 plus or minus square root of IX minus IY by 2 whole square plus IXY square will give you IU and IV. Then theta is the angle made by the YY axis with VV or XX axis with UU, right? So using these values, you can calculate tan alpha and alpha, the angle made by UU axis, the neutral axis with the UU axis, you can calculate. Now let us take a simple example. Now this is a symmetrical I section, which is used as a cantilever with the span of some 2.14 meters or something. It is given in the problem. So now the loading is applied along this axis. So I'm calling this as YY axis. So this is my XX axis, XX axis and YY axis. And this is UU axis and this is YY axis. So this is your theta. The plane of loading is a trace of plane of loading is making an angle 20 degrees with the YY axis. Okay. So now it has got two components. P is, well, it is 200 newtons. It is given as 600 here. In the next page, it is 200. So take it as 200. Correct it. 200 newtons is the load acting at an angle 20 degrees with the vertical and passing through the CZ of the section. So now it has got two components. So 200 or P cos theta, P cos 20 in the vertical direction, and P sin 20 in the horizontal direction. And if it is a cantilever, what is the, and if this load is acting at the free end, what is the bending moment? If a load P is acting at the free end of a cantilever of span L, you all know it is P into L, or W into L is the maximum bending moment which you get at the support. So now for this section, we will calculate what is IXX, which is incidentally IUU, which is, now you can calculate in different ways because it is a symmetrical section. Now you can take BD cube by 12, that is moment of inertia of the outer rectangle like this, BD cube by 12 minus about UU axis or X axis, right? BD cube by 12 of outer rectangle minus 2 times the moment of inertia of the inner rectangle, right? That will give you moment of inertia of net section. So that's what is being done here. 30 into 50 cube by 12 for the outer rectangle. This is 30 and total is 50. So 30 into 50 cube by 12 for the moment of inertia for the outer rectangle about XX axis or UU axis minus 28 into 45 cube by 12. So total is 30 and this is 2 millimeters. So this value and this value put together, the width, total width is 28, 30 minus 2. So 28 into B into D cube by 12. D is again 45. So 28 into 45 cube by 12. So this gives you IUU, IXX. Then IYY, it is, you have two flanges. About y-axis, the moment of inertia of each flange is 2.5 into d cube, 30 cube by 12, and two such areas are there. So 2 into 2.5 into 30 cube by 12 plus, this is from here to here, it is 45, the web portion, 45 into d is 2 cube by 12, 45 into 2 cube by 12. So this is IYY. Now after getting IUU and IYY, now this moment, if you calculate, it is W into L for the cantilever. W is the load acting at the free end, or P is the load acting at the free end of span L. WL is the moment. 2.4 meters is the span of the cantilever. 200 newtons is the load acting at the free end. So 200 into 2.4, 480 Newton meters is the moment. Which, had it been vertical, this would have been the moment. Now it has got two components. We have just now seen that m cos theta and m sin theta. M cos theta, which is along vertical plane, which acts about UU axis or XX axis, and m sin theta is acting about YY axis. So the two components, m dashed, m sin 20 is about UU axis. So mu by I by or IV into its distance. Again, if you go back, this moment when it is acting cos component, cos theta, m cos theta acting about XX axis or UU axis. So m cos theta divided by IXX into maximum distance from this UU axis or XX axis is, total is 50. So 50 by 2. From here to extreme fiber is 50 by 2. So we want to find the stresses at A, B, C, and D. At these points, at these corner points, you want to find the stresses. So distance of this point A or B from UU axis is 50 by 2, that is 25 millimeters, right? Similarly, when you calculate the other moment, m sin 20 is acting about YY axis. So m sin 20 divided by IYY or IVV into distance of extreme fiber from this axis, YY axis, is 30 by 2. Total is 30. So this is 30 by 2, 15. So these two you will get. So that is what is written here. M double dash into 25 into 10 power minus 3 by IXX plus m dash into 15 into 10 power minus 3 by IXX. This 10 power minus 3 is to convert it into meters. 25 mm. This is 15 mm. So into 10 power minus 3 will give you in meters. IXX and IVV also are to be used in millimeter to the power 4 moments of inertia. So take care of these units. Now we'll go to the signs. Let's go back again to the previous diagram. Now, when the vertical load is applied like this on the cantilever, how it bends in the vertical plane? Top convex and bottom concave. So top tension and bottom compression. So the moment about IUU produces tension top and compression bottom. Okay, so you can take tension positive or compression positive, but throughout the problem you should follow the same convention. If the net stress is positive, whatever you have assumed positive, it is that stress. If you assume it as, if it comes as negative, whatever you have assumed as negative, this stress is of that nature. Okay, so now this stress above UU is tensile and below UU is compressive. Similarly, when you take the moment about YY axis or VV axis, it is pushing the member from the left hand side. So it is pushing the member from the left hand side. So when a cantilever is pushed from the left hand side, it bends convex to the left and concave to the right. When it is pushed from the left hand side, it bends convex this side and concave this side. So to the left of it, convex means you get tensile stresses, and to the right of it, you get compressive stresses. Hope it is clear. So about YY axis, to the left of it, it is tensile, and to the right of it, it is compressive. So if you take A, the point A, it is above UU axis. above UU axis is tensile, below UU axis compressive, right? So A, due to moment about UU axis or MV, it is tensile. If you take tensile positive, the stress here is positive due to moment about UU axis or moment in the VV plane. Similarly, moment about YY axis or VV axis, if you take, it is to the left of it. Left it is tensile, right of this is compressive. So point A, due to moment about UV axis, it is tensile. Moment about VV axis also, it is tensile. So both the values you get positive. Is it clear? So A, it is above UU axis to the left of VV axis. So it is both tensile. Now coming to point B, it is above UU axis. So you get the stress as tensile because it is above UU axis. It is to the right of VV axis. Right of VV axis means it is compressive nature. Left of VV tensile, right of VV compressive. So right of VV now it is compressive. So moment about UU axis, you get tensile. The first one or tensile and second one compressive. So if you look at this, sigma A, both are tensile in nature. So this is plus, this also is plus. So it is net value is positive value. That means a tensile stress of 331.17 meganewton per millimeter square is the value which we have got. At B, this is tensile. About UU axis, it is tensile. About VV axis or XX axis, it is tensile. About YY axis, it is compressive. So this is plus, this is minus. And the net value is minus we have got. That means the stress is compressive in nature because tensile stress we have assumed positive. So the stress is compressive because it has got negative sign. You hope this is clear? Or let me explain again. Is it okay? So this is one problem. And again, another problem also you can do it. A T section. Shall we take it up in the next class? Okay. Then we'll continue in the next class. Now, I want the numbers of those students who are all present here.